Okay, this ball. I'm going to start over. I'm going to go through the very basics of a numerical calculation. How to solve problems. You don't actually have to use an electric computer, but we're going to use an electric computer. We're going to write a program to solve problems. Here's what I expect of you. I expect that you've looked at position, velocity, acceleration. You can do basic kinematic equations. That's all you really need to do this, okay? You don't need any programming experience. You don't need to know anything about that. I'm going to show you everything, okay? And I don't know how long this video is going to be. I never do. I just go, okay? So I want to be able to model the motion of this toss ball because we can do it on paper. And we can do it numerically. So we already know the answer. And then after that, we're going to look at something more complicated like this. Let me back up, see? A falling coffee filter, which is not the same as a falling ball. It's close, but it's not, okay? So let's start with the very basics of just looking at this problem. I'm dropping a ball. Let's say it fell a meter, okay? From rest, and it fell a meter. How would I solve that problem? Let's switch over here. Let me turn off this camera and let's just do that problem. It's not, I'm going to go through it fast, okay? Because I assume that we already know how to do this. And if you don't, that's fine too. I'm here to help you and you can rewatch this video and everything. So here I have a ball, has a mass m, and here's the ground. And when I let go, there's one force on it. We'll call that the gravitational force mg, where g is the vector, 0, negative 9.8, 0 newtons per kilogram. I'm going to mostly do this in one dimension, but I don't like to say things that are wrong. Okay, so I put that there. Now, I'm going to use the Newton's second law method for this. I would probably use momentum principle, but it's all good. Okay, so let's say this starts at some height h. I can put my y equals 0 meters down here. Then I know, let's just jump into the kinematic equation. I don't want to derive that for you. I can say y as a function of t is the initial y plus the initial y velocity times t plus 1/2 ay times t squared. Assuming t at t equals 0, it's at position y0 and velocity vy0. And so let's say, how long is this going to take to fall? Let's just solve something like that. So it's going to fall down here. How long does that take? So let's solve this for t. So my final y is going to be 0. My initial y is going to be h. My initial y velocity is 0. And then my accelerations in the y direction is negative 9.8. So it's going to be minus 1/2 g t squared. So let's add this to both sides. I get 1/2 g t squared equals h. If I solve this for t, I get t equals the square root of 2h over g. Okay. Now we're going to do the problem again. We already know the answer. I can put in h equals 1 meter and my value for g. Let's just go ahead and get the time. I actually have a calculator today. Look at that. Let's see. Put it right there. Turn this on, and I'm going to say 2 times 1. I'm not really good with calculators. Divided by 9.8. Oops. Clear. Okay. Let's do this. Square root 2 divided by 9.8 equals 0.4. That's not right. 0.45 half a second? Seems like it'd be longer than that, shorter than that. Let's just see, 0.45 seconds. I'm not good with calculators. Okay. Okay, now let's do it again. Let me start off with some very basic stuff. So here's my ball. There's the ground. There's my ball. I know that we define, and I'm going to deal with in 1D. Everything's in 1D. Okay. So we can first of all define the acceleration in one dimension as A is the change in velocity over the change in time. If the acceleration is constant, then this is true. Okay. I also can define the velocity. The average velocity is technically mostly true, is the change in y over the change in time. Now, let's do the following. Instead of letting this fall till it hits the ground, let's let it fall for 0.1 seconds. So I'm going to pick delta t is 0.1 seconds. So it's going to be right here. Now the question is, where is it and how fast is it going? Well, I can use these two equations up here to find that, right? I can use this, and let's say this is v1 equals 0, v2 equals, I don't know, y1 equals h, or 1 meter actually. We need to use actual numbers. Y2 equals, I don't know. Let's find y2 and v2. Okay, so up here, I can use the definition of acceleration. I can say a is v2 minus v1 over delta t. This is the change in velocity divided by the change in time. And I know what that acceleration is. It's negative g. So I can multiply both sides by delta t. And I can add v1. So I get v2 equals v1 minus g delta t. So let's go ahead and find that velocity. So I'm going to pull over my handy dandy calculator. So I'm going to say v1 is 0. Let's go ahead and put that in. 0 minus 9.8 times 0.1 equals. I get negative 9.98. So that's v2 equals negative 0.98 meters per second. Now what about y2? Here I can say v average is the change in y, which is y2 minus y1 over delta t. I can solve this for y2, and I get y2 equals y1 plus v average delta t. Okay, but what's the average velocity going from here to there? Well, I don't actually know that. I could find that out, right? I could just take half of that. It's not that hard. But I don't want to. I want to do this easier. I want to say, okay, I'm going to just say v average equals negative 0.98 meters per second. What the heck? Right? What the heck? I'm just going to do that. If I do that, I get y2 equals y1, which is 1. So I go clear 1 minus 0.98 times 0.1 equals. I get 0.902 meters. So I just found out where it went from 1 to 2 after 0.1 seconds. But it's not at the ground, right? Because this is not a 0. So what does that mean? Well, that means I have to do it again. I want to find out how long it takes to get to the bottom. I'm going to do this in 0.1 second steps. And how many steps am I going to have to do to get that? Okay, so let's just go ahead and break down a little chart here, because I think it's important to think about this as a chart. So here I have the following. Time, v, y. So I start off at time 0, v0, and this is in seconds. This is in meters per second. This is in meters. And this is at 1. That was my initial conditions. The next one, I had the time was 0.1 seconds, right? I increased it up there, and I got the velocity of negative 0.98, and I got the final position of 0.902. So now let's do the next row. This was going to be 0.2 seconds, right? Because it's going to be the next time step. So how do I find the next velocity? Well, let's write down v3 equals v2 minus g delta t, right? I can use the same definition of acceleration except use 2 and 3. So I'm going to take this velocity, I'm going to subtract 9.8 times 0.1, and I get my final velocity. So let's do that. Clear negative 0.98 minus 9.8 times 0.1 equals. And I get negative 1.96. Now I'm going to use this velocity with my position up here to find my next position. So I can say y3 equals y2 plus v3 delta t. So I'm not going to use the average velocity. I'm going to use the final velocity. That's cheating. Okay, but let's just see how it works out. Okay, so now I'm going to go use this velocity. I'm going to say y2 0.902. And then I'm going to say plus a negative, so minus 1.96 times 0.1, enter. And I get 0.706. It's still not to the ground. So then I'll do this again for 0.3 and 0.4 until I get to the ground. And that's how we do it. Okay, and I don't want to do that because I'm lazy. I'd rather do this if this is simple work, right? I just have a rule for how you find the next velocities. If there's a rule that says a computer can do it. Computers are all about rules. So let's do this in Python. Let's do this exact same thing in Python and see how it works. Okay. And again, you don't need to know anything about Python. You don't even need to install anything. I'm going to even give you the code. Okay. So let's switch over here to the computer. So this is Trinket.io. It uses Glowscript VPython. The one thing I like about this, there's another version over here. Let's just open that up. Let's show you the other version. Glowscript.org is another way you can do this. If I go over here and create a new program, this is for show, is for create. The one thing about this, it's actually the same idea, but you would have to log in order to edit this code, and it doesn't show the input and output side by side. So for that, I like Trinket because you don't even have to log in. You can come in here, once I give you the code, you can edit it and run it. It won't save, okay, but you can still do that. You can run it and change it and see what happens. So I like that. And it even runs on your phone. It's so great. I don't know what I'm talking about here. Okay, so let's make this a little bit bigger. Plus. Okay, so I'm going to say my first ball drop, even though it's not. And I'm going to save that. Okay, so let's just go ahead and make some variables here, right? We want to put in our initial conditions. So don't touch that Glowscript 3.1 VPython. You need that so that this will know to add some things in there that you need. So the first thing I'm going to do is add in my G. I'm going to say G equals 9.8. Okay, and I've already, that's my magnitude of the gravitational field because I'm dealing with this in one dimension. I can say Y equals 1 and V equals 0. Okay, now we can assign variables in Python. You can just call it whatever you want. Oops, that fell over. But you have to, it does matter what case it is. And you don't want to put a variable in there, a letter in there. If I say 1 meters per second, then it's going to treat that as something different than the number 0. And we want to just deal with the numbers. Python's not that smart. It can only do what we tell it to do. Okay. So let's just do this. I'm going to show you something that's very useful. Print G. Okay, let's run that. And it printed out G. Can I get this? There, let's do it like that. I hope that's not too small. Now I could also do something like new stuff equals 2 times G print stuff. So the print statement's really useful to get numbers out. You can make it more useful. If in this parentheses I can put quote stuff equals quote comma, and it'll print out the word stuff equals and then the number stuff. I can go down here and I can say, let's say I want to change G, right? I can say G equals 1.6. It's like Mars. Now I can say print 2 times G, and it'll do that, right? I can change the values of these things. Okay, so you can do plus, add, subtract. That's a good start. Okay, so let's do that. Let's just tell it what to do. So I'm going to say t equals 0, and then my delta t is 0.01. No, 1. Okay, so the first thing I'm going to do is exactly what I did. I started with my initial conditions right there. I'm going to calculate the position and the velocity after 0.1 seconds. So I'm going to say this. This is going to be weird. Watch this. V equals V minus G times dt. Print V. I'm going to run it. And there you see I got the same thing I got for the velocity. But you'll notice something really weird right here is that I have V equals V minus G times delta t. And it looks like the V's cancel. The V's do not cancel. Okay, this is not an algebraic equal sign. This is a make equal to sign. This tells Python, take G times dt, subtract that from V, and then make that the new V. So I don't need to do V1, V2, V3, V4. I just have to use that one variable for the velocity. Okay, so now let's do the same thing for y. Y equals y plus v times dt. Now you notice here's something very important, is that since this line 11 is after line 10, it's using the new value of v. That's why I used v2 in my equation before. I'm using the new updated v. If you switch the order of these, the calculation doesn't work as well, but that's something that you can explore later on your own. And so let's print y, v and y. I can do it like that. I won't put a label. There, so there's my v, there's my y. That's exactly what we got. Okay, now let's just do it. Now let's update time. So say t equals t plus dt. Oh, actually, that's, yeah, t equals t plus dt, and then I'll print out all three of these. T comma. Okay, so there I did it all. Now that was for first step. Let's do for the next step. If I want, I can just say copy, Control C or Apple C or whatever, paste, and run it again. Let's see what happens. So now we're at the 0.2 seconds. See, I've already told it how to do this calculation. I don't have to redo the calculation. I can just copy and paste it, and I can just keep doing this until this y gets to 0. I know you think that's not the right way to do it. Okay, now I'm at 0.4. The velocity is getting greater. So now I'm right here at 0.02. I'm almost at the ground. Okay, and it's at 0.4 seconds. Remember, we calculated a fall time of 0.45 seconds. So we're right there, right? It's not perfect, but we're right there. But let's do this a better way. What if I wanted to do this with a smaller time step? If I decrease that time step, then my answer is going to get better, right? Because my approximation that the average velocity is equal to the final velocity is better. So let's do that. If I change this to 0.01 and I run it, then these get smaller, but now I have to run a lot more calculations in order to get down to the bottom. So that's not good. I don't want to copy and paste forever, so we're going to introduce a loop. Let's do a loop. Okay, so I'm going to delete all this and that, and let's do a loop. So I'm going to say this: while t less than 0.06 colon. So this is a while loop in Python. This says as long as that variable t, which is at 0 right now, is less than the number 0.06, do everything that's indented below this. So watch this. I'm going to say t equals t plus dt. Some people got mad I didn't put spaces in here, but that's fine. And then I'm going to print t. Let's print t equals t. And I put unit seconds. Okay, so let's just run this and see what happens. So you'll see here it went through here. T was less than 0, so it added 1 to it, and then it printed the first one, and it went all the way up here to 0.06, and then it stopped because once it got to here, it went back up to the loop, and then it said, well, t is not less than 0.06, it's equal to 0.06, so it stopped. Okay. Now just so you can see here, I'll put this print. I stopped. Just so you can see that once it finishes that loop, and this is tab dedented, undented, it prints that last statement. So it stopped. So we can see where it stopped. Okay, so that's how a while loop works. So what we're going to do is just do this while, let's just pick a number. Let's do while t is less than 0.5, right? 0.5. Because I knew it fell for 0.45 seconds. And I'm going to tell it to do the following. Number 1, update the velocity. V equals V minus g times dt. And then I'm going to update the position. Y equals y plus v times dt. And then I'm going to print t. Let's just print the same coordinates again. So t, v, y. Okay, so we're going to get a ton of data right here. I'm going to get 50 lines, and they're all right there. But you can see right here, if I scroll up, when does it get to y equals 0? It's right here. See, right here it's at y is 0.0298, and then a little bit later it's at 0.0143. So somewhere between 0.4 and 0.45 would, what did I get for the time before when I solved it analytically? I got 0.45. Okay. So right around there I get to 0. Okay. So that's it. If you did this and you ran this, that's your first numerical calculation. Now, what's great about this, because it doesn't seem like you gain anything, but you're going to gain something in just a second. Okay, let's just go ahead and do this. What if I change the initial velocity to, let's say, 1. So it has a positive velocity in the upward directions. And I rerun it. I don't care, right? It's still going to run it for 0.5 seconds. But you notice now it's not at y equals 0. And if you scroll up here, one thing that's going to be interesting is this line up right here. At 0.1 seconds, the velocity is 0.02 and it's 1.046 meters above the ground. The next time, 0.11, it has a negative velocity. So this location is where it went from going upwards to going down. That is the highest location. So the highest it went was 0.04 something. Okay. Okay, now we need to, this printing out stuff is not fun. Okay, let's do something else. Let's make a graph. Okay, this is the easiest graph that you can make. This is part of what makes VPython so awesome, is that I can say f1 equals g curve. And f1 is just a name. You can call it whatever you want. I always do f1 for function 1. I don't know why. I learned that probably from someone else, and I just use it. So now down here, if I do that and run it, nothing's going to happen, right? Because I never printed anything. But if I go down here and I say f1.plot, and I can give it two variables, the x-coordinate and the y-coordinate. So if I want to plot time on the x-axis and position on the y-axis, I would say t, y. And now let's run this. And there you go. Check that out. You just made a graph. And not only that, I can look at this graph and tell what's going on, right? This is the vertical position as a function of time. So it goes up. Here's the highest point. I can actually get that time at 0.1. I already said that. And here's where it hits the ground, down here somewhere. And so I can get a lot of detail from that. Let's make the graph a little bit prettier though. If I go up here and say t graph equals graph, title equals projectile motion, x title equals time, y title position. This is called y. Also over here, I'm going to say width equals 500, height equals 350, just so it shows up on the graph. And now if I run that, see, I get a better graph. And it's still a little bit too big, but that's good. You like that? I like that. Okay. Now let's do one other thing. Let's run this and find out how long it takes to get to the ground. So I don't actually have to do a while loop as t greater than or less than or equal to 0.5. I could do this. I could say while y is greater than or equal to 0. This will do it as long as it's above the ground. And so let's do that. And let's go down here and say print t equals t seconds. So it ran it until it got back down to the ground. It actually went a little bit past that, right? That's okay. And I get a time of 0.5 seconds. And that's different than 0.45 because I threw it up. Okay, and I could change its velocity to whatever I want. I could change it to 5 and rerun it, and I get a different curve. That is a parabola, okay, in position time. I could plot y versus x. I could do, which in this case would be dumb, I could throw it horizontally. I'm going to stick to one-dimensional motion here, but that's your first numerical calculation. This is something, though, that you can do on paper, and you could get the same answer, okay? The smaller this time interval is, the better your answer will be. But at some point, if I make it 0.0000001, then I'm just wasting time. I'm not going to get a significantly better answer, but it's going to take longer to run. Okay, what about this? What's different about this? Let me switch over to the paper and let's talk about dropping an air filter. And I actually have some numbers for this. Let's see. Did I put those down here? Yeah, I do. Okay. Paper view right there. Okay, so let's drop a coffee filter. The one thing that's nice about these coffee filters is that they have a lot of air drag compared to their weight, so they fall at a constant velocity, sort of. So if I have this coffee filter falling, there's actually two forces acting on it. There's the downward gravitational force, mg, but then there's also an upwards air force. And you can feel that air force as you move your hand through the air. You can feel that it pushes in the opposite direction of motion. And so let's model this as F, the magnitude of the air force, as, I think I just put K V squared, where K, I've already measured this, and I think this works. And you could also write, often we'll do this, F air is 1/2 rho A C V squared, where that's the density of air, that's the that's the cross-sectional area, that's the drag coefficient, and that's the velocity. Okay, but it's in the opposite direction of the motion. So in this case, I actually measured the coffee filter drag coefficient in this, which would be all this stuff together, of 8.42 times 10 to the negative third newtons per meter squared per second squared. Yeah. And the mass of a single coffee filter, M1, is 0.0026 kilograms. So the question is, what if I take, let's say, 10 coffee filters, and I drop it? And I drop it a distance of, so I'm going to have this. There's my, that's not a coffee filter, that's a coffee filter. M equals 10 M1, V0 equals 0, and let's say this H is 5 meters. Okay, so pretty high, right? So in this case, it's not going to move at a constant velocity because it's got to speed up first. So as it speeds up, this force increases. And so I can't just calculate how long it takes to get to the ground. I mean, I can, but you're going to have to use differential equations. It's not so easy. So here's what we're going to do. I can say this. F net y is going to be F air minus mg equals ma. So let's put in my value for F air. And since it's falling down, this is always going to be up. So I can say K V squared minus mg equals ma. So if I solve this for the acceleration, I get A equals K V squared over m minus g. So I know my acceleration. Now if I break this into a delta t of 0.01 seconds, then what I can do is I can assume that this acceleration is constant, but it's not, right? Because as the velocity increases, the acceleration is going to actually get smaller because these two are working in opposite directions. Well, it's going to get smaller, negative. Yeah. So, but if I take a small time step and I assume that's constant, then I can use my same idea for my numerical calculation, and I can say V2 equals V1 plus A delta t. Just like I did before, right? The only step I'm adding here is calculating this velocity. And then I can use that and update the position. Y2 equals Y1 plus V2 delta t. And then I can update time. T2 equals T1 plus delta t. And then I go back up and do it all again, because now the velocity has changed, so my acceleration has changed. So the next time interval, I need to take that into account. And you could do this on paper, right? But if it takes 5 seconds to fall and break it into a 0.01 second, then you're talking about 500 groups of calculations, which you can do on a calculator. I just don't want to, right? You could also do this on a spreadsheet. You could do this in Java. You could do it Fortran, whatever. Okay, I'm just going to use Python. Okay, so let's do this in the program over here. And there's so much more to this stuff. Okay, we're just touching the surface. Just touching. Okay, so let's go ahead and make a new program. Let's save that. And I'll give you both of these programs. And remember, I'm dropping it from 5 meters high. I want to find out how long it takes to hit the ground. So I'm going to go up here. You can create an account on Trinket for free. And it has Python. If you do that, it has Python. The ones with the key, you have to have a paid account in order to save. But you could do Python for free. You could do HTML. Glowscript is the one you want. That's Python with the visual module in there. That's what you need to make the graphs. Then they do have a block version where you can drag things around, like in Lego Robotics, the old Lego Robotics. But I'm going to do this. Okay, so let's start off with, we're in one dimension still. Let's do coffee drop. And so I'm just going to say G equals 9.8. Let's go ahead and put this, newtons per kilogram. If you put a number sign, or as my kids say, a hashtag, then that's a comment. And so the computer will ignore that. But it's good for me to remember what those units are in, because those units actually do matter. Let's say V equals 0, Y equals 5, K equals a capital K, which what did I say it was? 8.42 times 10 to the negative 3. So in Python, e, lowercase e is scientific notation, so you can use that. And you could put a comment up here. You could do this. Drag coefficient for coffee, if that made you happy. Okay, and then let's call it M0 equals 0.00, what did I say it was? 0.0026 kilograms. Okay, now I need to make a graph. Tgraph equals graph. So the graph is a built-in object. Tgraph is just what I call my graph. You actually don't even need to give it a name. And I'll include a link down below for more graphing than you could possibly imagine. So title equals coffee filter. I should call it falling, but I don't want to. X title equals time in seconds. And then Y title equals Y in meters. And then let's do width equals 500. Actually, let's do a little bit smaller. 450. Height equals 300. F1 equals G curve. I'm going to put this as blue. I always like the blue. Color equals color.blue. You don't have to, but that will make that line blue. So G curve is a function that plots data points and it connects them by a line. There's other options in there. You could just plot the data points, but I'm not going to do that. Okay, I need t equals 0, dt equals 0.01. So I want to do this while the coffee filter is above the ground. So I'm going to say while y greater than or equal to 0, do the following. And the first thing I'm going to do, now I need to calculate that acceleration. That's my first step. It's not constant. So I'm going to say a equals, and I'm looking at my equation over here. I have k, capital K, times v squared. In Python, squared is star 2, not hat 2, okay? Minus g. So now I calculated the acceleration, and I'm going to do that in each loop of the thing. Now the rest is the same. V equals, should I put the spaces? V equals v plus a times dt. So now I'm using a instead of minus g, right? Because I have to actually calculate a. Now I can calculate my y. Y equals y plus v times dt, and then update time. T equals t. Okay, t equals t plus dt. Now I'm going to plot it. Oops. So let's add our plot in there. So f1.plot t y. I don't know, what do you think it's going to run? But look how short this program is, right? I have spaces in there. I have stuff that I don't really need. I don't even need to, I could cut this down even further, but it's not that much. But if it works, it works. So let's run it. And it worked. Oh, I didn't do this. Let's print out that final time. You could get the time off the graph right here by moving your cursor. But let's print that down. So let's say print t equals t, comma, seconds. Let's put s. Okay, there you go. What if I want to do something different? What if I want to plot the velocity as a function of time? Let's just do that for fun. Over here, I'm not going to change the title on the axis. If I just change that to v, check this out. So this says it actually is moving at a fairly constant velocity the whole way down. That's not that exciting. Oh no, it's decreasing. It's accelerating the whole way, right? Constant velocity would be like this. I did it wrong. I didn't divide by the mass, that's why. So I forgot this. Divided by m0 times 10, right? That was the mass of one filter. Okay, that looks better. So it speeds up, and then it does reach a constant velocity down here. Oh, you can't see because I put that on out of the way there. So it reaches some constant velocity down here. Nearly constant, that's terminal velocity, where the air drag is equal to the weight. So let's go back up here and plot the position, see what that says now. There, that was cool. So here you can see it's accelerating like a parabola, but down here it's fairly straight and linear, and then it takes 1.29 seconds. That's actually a pretty long time to fall from 5 meters. it would, but let's just try, right? What if there's a ball? What if I drop a ball? Well, I could do that. I could change this into a ball by changing the drag coefficient to 0. Right now, when I go down here, my acceleration is just going to be 0 times all this minus g, so I should just get negative 9.8 meters per second squared, and it takes 1.01 seconds. Actually, 5 meters is 25 feet high. That's pretty high. Okay. Save this, and I'm out. That was your first numerical calculation. You gotta practice to do this stuff. There's so much more that you can learn, and so much more great stuff that you can do. I should turn on my camera because that's important. And you should do it. Go in here, play with this, break it. Okay. Let me show you one thing though, because you can't break it. If you mess up something and you can't get it to run, you can always reload the page. But also up here, I think you can see it. If I click this and I go to reset, it'll go back to the way it was. Okay, if you wanna save it, you can make a copy over here and make a copy of it for yourself in your own account and save it, and then keep it and do whatever you want with it. So I'm going to show you some more stuff, but that's my very, very basic introduction to numerical calculations. It's not magic. It is legitimate, and there's so many problems that you can't solve except by doing numerical calculations. And Python makes a great platform for that. Okay, let's stop there because I'm tired, and you should be too. Okay, I'll talk to you later, and we'll do another video.